Hello. Hello.
Okay, I'm here.
So can you hear me?
Yes.
Okay, so please just review the solution and then we can close the first day.
Okay. Let me see on my solution. Okay, can you guys see my screen?
Yes, everything is perfect.
Okay. Okay, let's call it the day. Let's try to show you the solutions. So this novel is quite advanced level of 6. Oh, so Fields is about the quantum chemistries, give you a bird's eye view about quantum chemistries. Okay, I will go directly to the solutions. Yeah, how to use the classical package to solve the. I mean, yeah, that's the classical method to show the quantum chemistry problem in classical computer. But also they also provide us some how to say pre-calculated information that we can use to fit into the data, like the initial guess about for the answers. Yeah, that's also some helpful. Like we use the classical computer to this package to pre-calculate some approximation or some initial guess. And in SQD answers, we need fit initial parameter because you see we use some rotational gate that require the rotational angle, and that angle, how we choose that angle has depends on us. I mean, it really depends on us. We can choose from randomly, or we can utilize the information um, from from the problem, or from classical guess. Yeah. Okay, so the first exercise is how you identify the number of electron spin up and electron spin down. So basically, it's because in the nitrogen molecules, so the spin up and spin out they are equal. So basically, you uh, when you get information about number of electrons using these functions uh, with the and with this total electrons for the nitrogens, and divided by 2, you will get the um, electron spin up and electron spin down. This one is redundant. I mean, not necessary. I mean, in the case of nitrogen, this just gives us the information about this one. This slide just gives us information about the difference between spin up and spin down. Number, yeah, the number different, the different number. So in oxygen, so this non-zero, but in nitrogen is zero, so it's not necessary. Yeah, but in oxygen we need to count it toward to get the spin up and spin down number. So yeah, this is exercise about quantum chemistry, and we need this information to fit into our answers. Yeah, it's the classical method people often use in quantum chemistry. Yeah, in chemistry to calculate the rough states. So here we can get the exact rough state from this package. But yeah, you should know that in the larger molecular, in the larger space with a more complicated molecular, that's not the easy way to. Yeah, that's the not easy way to use this method to solve the complicated molecule. Yes, the T1, T2 is the information to fit into our SQD answers. So it's recommended to watch this video about the sample place SQD method. Okay. For the exercise 3, we try to create a real amplitude hardware efficient answer for SQD. And because it's hardware efficient, because it's you very few and very few and non, let's see, non cross local quantum gates, like 1 or 2 qubit quantum gates, and is efficient and efficient in noise way that is resilient to the noise, reduce the noise effect in our answers. So you see here basically is you just use some rotational gates and some CNOT gates. Yeah, it's quite a lot, but it's the more hardware efficient answers in the quantum chemistry problem. If you look at the UCC couple cluster answers, or the other one that use the dynamic the dynamic information from the Hamiltonians, the answers look like really cumbersome and complicated. So it's still quite simple. The execute circuit, yeah, we already get to know in the previous notebook. So if you don't, just go back to the previous notebook to have your idea. Process and analyze results. As I explained before, we divide into from the configuration sample from our quantum circuits. We divide them into different batches, and from each batch we have some samples, and we project the full Hamiltonian into the sample configuration, and we get a small, relative smaller than before, Hamiltonian. and we can use the classical diagonalize method to diagonalize the Hamiltonian. So that's all. Yeah. So we call the diagonalized fermionic Hamiltonian function and fit into some data. Okay, so we will get the result. So this is the energy error convergence. So it will, after 4 configuration iteration, recovery iteration, we will get the error drop down below the chemistry's accuracy required. Yeah, the required chemistry accuracy, and the orbital, the occupancy orbital index you show here. That shows how the electron, how the probability how electron occupy the orbital, and then we will try to play around with the UCJ, how to say, unitary cluster answers that inspired from the Hamiltonian, inspired directly from the problem. We get the information from the Hamiltonian. Yeah, like I said before, if you just build arbitrary answers, so it's like you randomly choose the configuration, not any specific reason. So that's quite uh, mm, unreasonable when you just choose random. So you don't know which, yeah, you don't know any guided choice, which one is right or which one is wrong, what should you, which direction you should go. So so this answer is kind of chemistry inspired, or I call it Hamilton inspired answers. Yeah, we get the information directly from the problem, and that's also we need to fit the our Hamiltonian or our problem into the answers. So as you see here, we we need to fit into number of orbitals, interaction pairs of our Hamiltonian, like yeah, like the electron up and down index, and we construct the unitary cluster answers from these code lines and execute. We will see the, yeah, relatively better one. Yeah. See, after it's converged at its first step. Yeah. Let's see, is for power 4 first step convergence. So yeah, it's relatively better. And you will see here, I said before, the answers is constructed from the rotational gauge requiring angle rotation, right? But here we just fed randomly the rotational gauge. This you may raise a question about, so what should be the right angle or the efficient initial angle we use. So that comes us to the next answers we call the informed approach. I mean, this means the informed angle or informed initial guess for the answer. So that's the T1, T2 that I showed you. I showed you before. Yeah. So, okay, I will go through this. So basically, you will use this function that so that's the result above here to get the information that technically pre-calculating by the classical method, and then contrast the answers and okay, execute. Okay, okay. That's my problem. As expected, it should be better performance than the previous two, but somehow I still have no idea why it look it looks like this. But it should be better than the previous two. Um, and if you look at the notebook from Qiskit IBM, and but they executed this method in the real quantum hardware, and it showed a better performance. Indeed, yeah, I also try to let you play around with the real hardware and or with the IBM Qiskit primitive, but maybe it's not the good way because not all of you have the Qiskit account, and it's quite a subtle thing to let on participant do with the Qiskit primitive. So that's why I try to use the pay packet, and somehow it's not my expectation. So basic. Okay, to summarize the results, so you will see the real hardware in the blue line, and the unitary cluster is shown in the orange line, and it shows better performance if you utilize the information from the dynamic information from the problem and okay, so for further study and deeper study, maybe it's also there also another method that's a sample pack SKQD is another SQD method. It's kind of variant of SQD method, but we need to implement on the real hardware because the the space for the SQD is quite large, and it's impossible to run on the classical simulation. It's not enough uh, memory to run the SQD. So that's why I cut out that exercise part and just leave you to do with the basic one. So yeah, for you can try to play around with SKQD. Look at the notebook in the IBM. And as I said before, you also can try to build a hybrid loop for the SQD, because here it's just one line SQD methods. When we prepare the answers, sample the answers, you get the configuration and diagonalize the Hamiltonian from that subspace configuration. That's all. But how about we try to build a hybrid loop that when you get the graph stack, but do are are you sure that's the exactly graph stack, or is the desired accuracy you want? So try try to optimize um, the initial angle, I said before, because initial angle is dependent freely in your choice. So try to optimize the initial angle and put it in the hybrid quantum classical loop. Maybe you will get the better results and the accuracy get the desired accuracy. Okay, so I think that's all for today. So thank you for your participant, and hope to see you tomorrow with the more interesting lectures. Thank you very much.
Yeah, thank you, Lee. Thank you for all speakers, on the instructor, and on the participant for giving us your time today. And we have a very beautiful day, beautiful lecture. I hope that you enjoy everything, every single moment that you had today with us. And see you tomorrow.
Okay, thank you.
Thank you. See you tomorrow for all of you. Yeah, bro. Chi là? Je vais mettre la fin de event. Mais c'est